Recurrence relations part 2. In the last session, we have seen how to find a solution of homogeneous and non-homogeneous recurrence relations. We note that a solution of a non-homogeneous recurrence relation is the sum of solution of the associate homogeneous recurrence relation and particular solution. We have studied to find particular solutions if Fn is the combinations of the polynomials and power of constants. Next, we are concerned with the question of finding particular solutions of recurrence relations. An is equal to C1 into An minus 1 plus C2 into An minus 2 plus etc. plus Ck into An minus k plus Fn with the different types of f of n. The method of undetermined coefficients. The method of undetermined coefficient is based on assuming a trial form for the particular solution AP of the recurrence relation An is equal to C1 An minus 1 plus C2 An minus 2 plus etc. plus Ck An minus k, which depends upon the form of the function Fn and which contains a number of arbitrary constants. This trial function is then substituted into the given recurrence relation and the constants are chosen to make a solution. The basic trial forms are given in the table as shown. C denotes a constant in the expression of f of n and A with or without subscripts denotes a constant to be determined. So, here we have Fn is equal to C and the respective trial A and P is A. Similarly, Fn is equal to C into sin alpha n, where the trial A and P is An into cos alpha n plus A2 into sin alpha n. Problem. Consider the recurrence relation An plus 2 plus 4 An is equal to 6 into cos n pi by 2 plus 3 into sin n pi by 2. Solution. The associated linear homogeneous equation is An plus 2 plus 4 into An is equal to 0. The characteristic equation of this recurrence relation is r square plus 4 is equal to 0 with roots r1 is equal to 2i and r2 is equal to minus 2i. Hence, the solutions to this recurrence relation are of the form Ah is equal to alpha 1 into 2i all raised to n plus alpha 2 into minus 2i all raised to n, which is equal to 2 raised to n into alpha 1 into I raised to n plus alpha 2 into minus I raised to n, which is equal to 2 raised to n into alpha 1 into cos pi by 2 plus I sin pi by 2 whole raised to n plus alpha 2 into cos pi by 2 minus I sin pi by 2 whole raised to n. Ah is equal to 2 raised to n into alpha 1 into cos n pi by 2 minus I into sin n pi by 2 plus alpha 2 into cos n pi by 2 minus I into sin n pi by 2. That is Ah is equal to 2 raised to n into alpha 1 plus alpha 2 cos n pi by 2 plus I into alpha 1 minus alpha 2 into sin n pi by 2. That is Ah is equal to 2 raised to n into C1 cos n pi by 2 plus C2 sin n pi by 2. For a particular solution, we try AP is equal to A1 cos n pi by 2 plus A2 sin n pi by 2. Now, An plus 1 P is equal to A1 cos n plus 1 pi by 2 plus A2 sin n plus 1 pi by 2. That is A1 into cos n pi by 2 cos pi by 2 minus sin into n pi by 2 sin pi by 2 plus A2 into sin n pi by 2 cos pi by 2 minus cos n pi by 2 into sin pi by 2, which is equal to A2 into cos n pi by 2 minus A1 into sin n pi by 2. Now, An plus 2 P is equal to A1 into cos n plus 2 pi by 2 plus A2 into sin n plus 2 pi by 2. That is equal to A1 into cos n pi by 2 into cos pi minus sin n pi by 2 sin pi plus A2 into sin n pi by 2 cos pi minus cos n pi by 2 into sin pi, that is equal to minus A1 cos n pi by 2 minus A2 sin n pi by 2. It follows that An plus 2p plus 4 Anp is equal to 3 into A1 cos n pi by 2 plus 3 into A2 sin n pi by 2, that is equal to 6 into cos n pi by 2 plus 3 into sin n pi by 2. Then a1 is equal to 2 and a2 is equal to 1. Hence, an is equal to ah plus ap, that is equal to 2 raised to n into c1 cos n pi by 2 plus c2 sin n pi by 2 plus 2 into cos n pi by 2 plus sin n pi by 2. Generating functions. Generating functions are used to represent sequences efficiently by coding the terms of a sequence as coefficients of powers of a variable x in a formal power series. Generating functions can be used to solve many types of counting problems, such as the number of ways to select or distribute objects of different kinds subject to a variety of constraints. Generating functions can be used to solve recurrence relations by translating a recurrence relation for the terms of a sequence into an equation involving a generating function. This equation can then be solved to find closed form for the generating function. From this closed form, the coefficients of the power series for the generating function can be found, solving the original recurrence relation. We begin with the definition of the generating function for a sequence. The generating function for the sequence a0, a1, etc. ak of real numbers is the infinite series gx is equal to a0 plus a1x plus etc. plus ak x raised to k is equal to summation k equal to 0 to infinity ak into x raised to k. Example, the generating functions for the sequence ak with ak is equal to 3 and ak is equal to k plus 1 and ak is equal to 2 raised to k are summation k equal to 0 to infinity 3 into x raised to k, summation k equal to 0 to infinity k plus 1 into x raised to k, summation k equal to 0 to infinity 2k into x raised to k respectively. We can define generating functions for finite sequences of real numbers by extending a finite sequence a0, a1, etc. an into an infinite sequence by setting an plus 1 is equal to 0, an plus 2 is equal to 0 and so on. The generating function gx of this infinite sequence an is a polynomial of degree n because no terms of the form aj x raised to j with j greater than n occur, that is gx equal to a0 plus a1x plus etc. plus an x raised to n. Problem: what is the generating function for the sequence 1 1 1 1 1 1? Solution: the generating function of 1 1 1 1 1 1 is 1 plus x square plus x raised to 3 plus x raised to 4 plus x raised to 5. Example: let m be a positive integer. Let ak is equal to cmk for k is equal to 0, 1, 2, etc. m. What is the generating function for the sequence a0, a1, etc. am? Solution: the generating function for this sequence is gx is equal to cm0 plus cm1 into x plus cm2 into x square plus etc. plus cmm into x raised to m. The binomial theorem shows that gx is equal to 1 plus x whole raised to m. When generating functions are used to solve counting problems, they are usually considered to be a formal power series. Questions about the convergence of this series are ignored. However, to apply some results from calculus, it is sometimes important to consider for which x the power series converges. The fact that a function has a unique power series around x equal to 0 will also be important. Generally, however, we will not be concerned with questions of convergence or the uniqueness of power series in our discussions. Readers familiar with calculus can consult textbooks on this subject for details about power series, including the convergence of the series. Next, some useful generating functions. Example: the function f of x is equal to 1 by 1 minus x is the generating function of the sequence 1 1 1 etc. because 1 by 1 minus x equal to 1 plus x square etc. for mod x less than 1. Example: the function f of x equal to 1 by 1 minus ax, the generating function of the sequence 1 a square, a cube etc. because 1 by 1 minus ax is equal to 1 plus a square plus etc. when mod Ax less than 1, or equivalently for mod x less than 1 by mod A for A not equal to 0. We will now give some useful generating function for the purpose of next section. 1 plus x all raised to n is equal to summation k equal to 0 to n c n k x raised to k, that is equal to 1 plus c n 1 into x plus c n 2 into x square plus etc. plus x raised to n. 1 plus Ax all raised to n is equal to summation k equal to 0 to n c n k into a raised to k into x raised to k, that is equal to 1 plus c n 1 Ax plus c n 2 a square x square plus etc. plus a n x raised to n. 1 by 1 minus x square is equal to summation k equal to 0 to infinity k plus 1 into x raised to k, that is equal to 1 plus 2x plus 3x square plus etc. 1 by 1 minus Ax all raised to n is equal to summation k equal to 0 to infinity c n plus k minus 1 k a raised to k x raised to k, that is equal to 1 plus c n 1 Ax plus c n plus 1 2 a square x square plus etc. e raised to x is equal to summation k equal to 0 to infinity x raised to k by k factorial, that is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. Using generating functions to solve recurrence relations. Now that we know generating functions, let us see how we can use them to solve recurrence relations. We can find the solution to a recurrence relation and its initial conditions by finding an explicit formula for the associated generating function. Example, solve the recurrence relation ak is equal to 3 ak minus 1 for k is equal to 1, 2, 3 etc. and initial condition a naught is equal to 2. Solution. Let gx be the generating function for the sequence ak, that is gx equal to summation k equal to 0 to infinity ak into x raised to k. First note that x into gx is equal to summation k equal to 0 to infinity ak into x raised to k plus 1, that is equal to summation k equal to 1 to infinity ak minus 1 x raised to k. Using the recurrence relation, we see that gx minus 3x into gx is equal to summation k equal to 0 to infinity ak into x raised to k minus 3 into summation k equal to 1 to infinity ak minus 1 into x raised to k, that is equal to a naught plus summation k equal to 1 to infinity ak minus 3 into ak minus 1 into x raised to k, that is equal to 2. Because a naught is equal to 2 and ak is equal to 3 ak minus 1. Thus, gx minus 3x gx is equal to 1 minus 3x into gx, that is equal to 2. Solving for gx shows that gx is equal to 2 by 1 minus 3x. Using the identity 1 by 1 minus ax is equal to summation k equal to 0 to infinity a raised to k into x raised to k, we have gx is equal to 2 into summation k equal to 0 to infinity 3 raised to k into x raised to k into k, that is equal to summation k equal to 0 to infinity 2 into 3 raised to k x raised to k into k. Consequently, ak is equal to 2 into 3 raised to k. Problem. Solve the recurrence relation system a naught is equal to 1 and a n is equal to a n minus 1 plus n for n greater than or equal to 1. Let gx is equal to summation n is equal to 0 to infinity a n x raised to n be generating function. The given relation is of the degree 1. So, multiply both sides of the recurrence by x raised to n and sum over n greater than or equal to 1. This gives summation n is equal to 1 to infinity a n into x raised to n is equal to x into summation n equal to 1 to infinity a n minus 1 x raised to n minus 1 plus summation n equal to 1 to infinity n into x raised to n. Now, summation n is equal to 1 to infinity n into x raised to n is equal to summation n equal to 0 to infinity n into x raised to n, that is equal to x into summation n equal to 0 to infinity n into x raised to n minus 1 is equal to x into 1 by 1 minus x whole square. Thus, in term of gx, we obtain gx minus 1 is equal to x into gx plus x into 1 by 1 minus x whole square. Rearranging terms, we get 1 minus x into gx is equal to 1 plus x into 1 by 1 minus x whole square. Hence, gx is equal to 1 by 1 minus x plus x into 1 by 1 minus x whole cube. Next, we are using the generating function 1 by 1 minus ax all raised to n is equal to summation k equal to 0 to infinity c into n plus k minus 1 k a raised to k x raised to k. We can now get a n by expanding gx as a series. Gx is equal to summation n is equal to 0 to infinity x raised to n plus x into summation n equal to 0 to infinity c n plus 2 n x raised to n. This gives a n is equal to 1 plus c n plus 2 n. Before considering next problem, let us note the following identity that is valid for any distinct numbers b and c. 1 by 1 minus bx into 1 minus cx is equal to 1 by b minus c into b by 1 minus bx minus c by 1 minus cx. It can be directly verified by taking common denominators of the terms on the right hand side and simplifying the expression. Now consider next problem and we will use this identity to solve. Consider a naught is equal to a1 is equal to 1 and a n is equal to n minus 1 plus n minus 2 for n greater than or equal to 2. Let gx is equal to summation n is equal to 0 to infinity a n x raised to n be generating function. As in the previous problem, let us multiply the recurrence by x raised to n and sum over n greater than or equal to 2. This gives summation n is equal to 2 to infinity a n into x raised to n plus summation n is equal to 2 to infinity a n minus 1 x raised to n plus summation n is equal to 2 to infinity a n minus 2 x raised to n. That is, summation n is equal to 2 to infinity a n x raised to n is equal to x into summation n is equal to 2 to infinity a n minus 1 x raised to n minus 1 plus x square into summation n is equal to 2 to infinity a n minus 2 x raised to n minus 2. In terms of gx, we have gx minus a naught minus a1x is equal to x into gx minus a naught plus x square into gx. That is, gx minus 1 minus x is equal to x into gx minus 1 plus x square into gx. This leads to gx is equal to 1 by 1 minus x minus x square. It remains to expand gx into power series so that we can identify a n. Now, note that 1 minus x minus x square is equal to 1 minus x plus x square by 4 minus 5x square by 4, that is equal to 1 minus x by 2 whole square minus root 5 by 2x whole square, that is equal to 1 minus x by 2 minus root 5 by 2 into x into 1 minus x by 2 plus root 5 by 2 into x, that is equal to 1 minus bx into 1 minus cx, where b is equal to 1 plus root 5 by 2 and c is equal to 1 minus root 5 by 2. Now, we can expand gx as gx is equal to 1 by 1 minus bx into 1 by 1 minus cx, that is equal to b by b minus c into 1 by 1 minus bx minus c by b minus c into 1 by 1 minus cx, that is equal to b by b minus c summation n is equal to 0 to infinity bx all raised to n minus c by b minus c into summation n equal to 0 to infinity cx all raised to n, that is equal to 1 by root 5 into summation n equal to 0 to infinity b raised to n plus 1 minus c raised to n plus 1 the whole into x raised to n. Thus, for all n greater than or equal to 0, we have a n is equal to 1 by root 5 into 1 plus root 5 by 2 whole raised to n plus 1 minus 1 minus root 5 by 2 whole raised to n plus 1. For n is equal to 0, 1, this formula gives a naught is equal to 1 and a1 is equal to 1 as was to be expected. Recursive algorithms. Sometimes we can reduce the solution to a problem with a particular set of input to the solution of the same problem with smaller input values. For instance, the problem of finding the greatest common divisor of two positive integers a and b, where b greater than a can be reduced to finding the greatest common divisor of a pair of smaller integers, namely b mod a and a, because GCD of b mod a comma a is equal to GCD of a comma b. When such a reduction can be done, the solution to the original problem can be found with a sequence of reductions until the problem has been reduced to some initial case for which the solution is known. For instance, for finding the greatest common divisor, the reduction continues until the smaller of the two number is 0, because GCD of a comma 0 is equal to a when a greater than 0. Definition: an algorithm is called recursive if it solves a problem by reducing it to an instance of same problem with smaller input. Example: give a recursive algorithm for computing n factorial where n is a non-negative integer. Solution: we can build a recursive algorithm that finds n factorial where n is a non-negative integer. Based on the recursive definition of n factorial, which specifies that n factorial is equal to n into n minus 1 factorial when n is a positive integer, and that 0 factorial is equal to 1. To find n factorial for a particular integer, we use the recursive step n times, each time replacing a value of the factorial function with the value of factorial function at the next smaller integer. At this last step, we insert the value of 0 factorial. The recursive algorithm we obtain is displayed as algorithm 1. To help understand how this algorithm works, we trace the steps used by the algorithm to compute 4 factorial. First, we use the recursive step to write 4 factorial is equal to 4 into 3 factorial. We then use the recursive step repeatedly to write 3 factorial is equal to 3 into 2 factorial, 2 factorial is equal to 2 into 1 factorial, and 1 factorial is equal to 1 into 0 factorial. Inserting the value of 0 factorial is equal to 1 and working back through the steps, we see that 1 factorial is equal to 1 into 1 is equal to 1, 2 factorial is equal to 2 into 1 factorial, that is equal to 2, 3 factorial is equal to 3 into 2 factorial, that is equal to 3 into 2 is equal to 6, and 4 factorial is equal to 4 into 3 factorial, that is equal to 4 into 6 equal to 24. Now, let us summarize what we have learned. We have studied various methods to solve a non-homogeneous recurrence relations. We also have tried to find particular solutions for different cases. We recalled the definition of generating functions and used it to solve recurrence relation. Recurrence algorithm with suitable example is also explained. Here are some problems to work out. First one, solve a(n) is equal to a(n minus 1 plus 2n minus 1 with a1 is equal to 1. Second, in bell ringing, successive permutations of n balls are played one after another. Following one permutation pi, the next permutation must be obtained from pi by moving the position of each ball by at most one place. For example, n is equal to 4, the permutation 1, 2, 3, 4 could be followed by any one of 2, 1, 3, 4, 2, 1, 4, 3, 1, 3, 2, 4, 1, 2, 4, 3. Show that if a(n) denotes the number of permutations which could follow 1, 2, etc. n, then a(n) is equal to a(n minus 1 plus a(n minus 2 plus 1. Hence, find a(n). Third one, use generating functions to solve the recurrence relation ak is equal to 4 into ak minus 1 minus 4 into ak minus 2 plus k square with initial conditions a0 is equal to 2 and a1 is equal to 5. Fourth one, use generating functions to solve the recurrence relation ak is equal to ak minus 1 plus 2 into ak minus 2 plus 2 raised to k with initial conditions a0 is equal to 4 and a1 is equal to 12. Now, I can suggest some books for further reading. First one, Elements of Discrete Mathematics, 2nd edition by C.L. Liu, McGraw-Hill International Edition, Computer Science Series, 1986. Second, Concrete Mathematics, A Foundation for Computer Science by Ronald Graham, D. Knuth and O. Patashik in 1989. Third one, Mathematical Structures for Computer Science, Judith L. Gersting, 1993, Computer Science Press. Fourth one, Applied Discrete Structures for Computer Science by Doerr and Levasher, 1985. Thank you for listening this session. We will see next time. Until then, goodbye.